Sir,
Yeah. Uh, so, Good evening, everyone. So,
sir,
this
wouldn't be solving the paper yesterday what we got this one.
the quiz one paper. Okay.
Hmm.
Uh, Maybe we'll
One and
do that on. Sorry. Maybe we'll do that one on Wednesday.
okay,
Is that fine?
okay, okay.
Yeah. Okay. So this week, good evening, everyone. So this week we'll be starting the module 5, lecture 1. So what we will do is in today's session, we'll try to revisit the content. Okay. Then Wednesday, as I said, so we'll discuss the paper, question paper, and then again continuing on Friday, we'll have the problem session on this module 5 on all the lectures. Okay. So basically, control systems. So these are the for any control engineer. So these are the major uh, concepts or major aims. So such as stability, tracking, regulation, and sensitivity. So particularly any control problem. Okay. So they will be connected to all these four aspects. Particularly any the aim of any control problem to reach to make the system stable, to have the tracking and regulations. So if you see that problem, so either it could be a regulation problem or it could be a tracking problem at the outset. Okay, so what we do in this lecture is, so first we will see what are these four problems with respect to this open loop and closed loop systems, and we'll try to see by considering an example what exactly these four things are. Then we will analyze the systems and try to see how to and getting into the concepts of designing the controllers to achieve these four tasks. Okay, so what we will do is first we will start at the basic level with the open loop system or open loop control. Then we will see what are these four concepts with respect to this open loop control. Then we'll continuing our discussion with the closed loop or feedback control. Okay, so that we'll have a uh, uh, simple clarity on what is happening when we shift from the open loop to closed loop. Okay, so as you know that open loop will be we don't have any feedback. So open loop will be having the reference signal, then actual output, then we have our system here. Okay, then this is the controller. Okay, so there will be no closure signal from output to the input. Okay, so here basically what this controller will do is, so it modifies this reference signal. So what we do is we give this reference signal to the controller. So the controller, it modifies the reference signal. Then after that, it will apply that signal to the system or plant. So this also called as the plant. Okay, so what this controller basically does is it takes the reference input and sometimes it may cancel the unwanted dynamics of the plant and try to replace them with the desirable dynamics to the plant. Okay, so you can have the various examples like washing machines, traffic lights, so etc. Okay, so the aim of this controller is it takes the reference signal, modifies the reference signal, and then it will give that as the input to the plant. Okay, so in reality, we may add this disturbance also. So first we will see in both the cases without disturbance and with the disturbance. Okay, so let's start with the open loop control system. So most of the open loop systems are they are very prone to the disturbances. Okay, so output is largely affected by the system parameters. Okay, so if you consider any of the electronic circuits, okay, so they are mostly affected by the system parameters such as resistor, inductor, and capacitors. So you could see from the previous uh, here. So what is the output here of a open loop system? So you are giving this reference input to this controller. So here you will get RGC. Then you have a summing point here. So that summing point will add this RGC and D here. So we'll give a signal of here. So RGC plus D. That will be multiplied with G. So here it will be like G multiplied RGC plus D. That is the open loop output. Okay, RGC plus D multiplied G. Okay, so once you have that, so what is the signal you wanted to get at output to reference input is R. So obviously the error is going to be what? Y minus R. So R minus reference minus output of the open loop system. So this one. Okay, once you take that, this is the expression of the error. Okay, for the open loop system with the disturbance. Okay, so we are starting with those four concepts. So let's see this example. So this is the example of a thermal control system where we have this system transfer function of this. Okay, so transfer function from heater to the output temperature. Okay, so here our goal is to uh, track the reference input. Okay, so the reference input R of t. Okay, so which is a reference input R of t is a ramp with a slope of 30 degree per second. So that will go for a duration of 30 seconds, and at steady state we should get a value of 300 degree Celsius. Okay, so this should be something like this. So this red one, this is our R of t. It is a ramp from 0 to 30 seconds with a slope of 30 degrees per Celsius. Then from 30 degrees onwards, it is 300. Okay, that is our reference signal. Now we wanted to design this open loop control. We wanted to design this open loop control. So in such a way that we wanted to reach this one. We wanted to track this reference signal R of t. Okay, so now simplest idea is this. We wanted to get 300 here. So usually what we do is, so 1000 multiplied by 0.3 will give us the 300. So the basic simple idea is just multiply, right? So take a input of 0.3. Okay, take an input of 0.3, and if it gets multiplied with g of s, okay, so we would get a steady state value of 300. Somebody asked a question. I don't think so. Okay, so we'll get a value of 300. Okay, so that is the basic idea, basic input we can take. Okay, so now if you take like that, okay, so here our main aim is to follow this R of t, red colored, this one. Okay, so what system has to do is the system must minimize the tracking error. Okay, it means that between blue and red, where blue is the controlled output after applying that 0.3. Okay, so red is the reference input. So our controller must minimize this tracking error. Okay, so and at the end it has to get 0. So this is the tracking error. As we go on for taking that 2.3 input, so the system tracking error is getting increased, and it became maximum here. Okay, and then slowly starts reducing. Okay, it is going to this almost equal to 0. That is for open loop case. Okay, so here, so that is the tracking error. So now a regulation. So basically regulation is defined as uh, your actual output of the system y of t. So to follow a specific value, to follow a specific value. It means that it will be something like you have t, you have y of t. Okay, so this value, let's say this is some kind of 1. Okay, so your y of t has to follow or has to reach this one reference value, that is called as the regulation. Okay, so you can see here regulation is the ability of the system to maintain a constant output value. Okay, so despite the external disturbances. Okay, so the problem of regulation is to keep the error very small, error between these two, it has to be very small when the reference is uh, at most the constant set point and disturbances are present. Okay, you wanted to minimize that error. When you consider the open loop system, okay, the controller will have no influence on all the system to either the disturbances or the noise. Okay, so why? Because the controller cannot do anything with the cannot affect these noise or the disturbance. So the open loop control system is not suitable for the regulation of this particular thermal system. Okay, so if you see this above example of the tracking error, okay, so if you consider a disturbance of step in nature, that is d of s is 1 by s. Okay, so the system output with the open loop proportional controller won't be able to attenuate that disturbance. So it means that still that this tracking error would exist. You can see here. So this tracking error would exist in all the points. So you cannot make that one to 0 because the controller will not affect the disturbances. Okay, that same thing you can see here. So for taking your d of s as 1 by s. Okay, when you take d of s as 1 by s, you can see so the error with no disturbances, so this black one, and with the disturbance of 1 by s, so this one. So you're getting the error here 0, here is 50. Okay, so in the temperature values also here you can see. So this is the 300 temperature you wanted to reach when you have no disturbance. Okay, so that is reaching exactly, but when you have the disturbance, you have this error at the steady state. Basically regulation means to reach this 300 value. Okay, whereas this open loop controller will have no control over the disturbance. Okay, we are getting this error at the end. Okay, so next is out of all those four, we have seen the tracking error, we have seen the regulation, and next is stability. Okay, so in the previous modules, I think in week 3 or week 4, we have seen what is called as the stability. Okay, so the stability is it is defined as the all poles of the uh, transfer function, they must lie in the left of the S plane. It means that if you consider this is the real part of the S and this is imaginary part of the S. Okay, so the if you find the poles of a transfer function, all poles must exist in the left of the S plane. Okay, this is LHP, this is RHP. Okay, so how can you define the poles if you consider a transfer function? So g of s, okay, where it has the numerator as well as the denominator. So if you take the characteristic equation, that is d of s equal to 0, that is denominator equal to 0, and then find the roots of this, these are called as the poles. Okay, these poles, they must lie in the left of the S plane of left of plane of the S plane. Okay, this is our S plane. Okay, if all poles exist on the left side, we say that system is stable. Even if one pole is existing on the right side, so we say that system is unstable. Now you see in the open loop system, so we have plant transfer function of G of S and controller is GC of S. How do they connected? They connected like this. This is G of S and here we have GC of S. Correct. So here we have reference input and output. Okay. So what is the overall transfer function? That is multiplication of these two. Okay. So you can write to G of S as B of S by A of S, GC of S as C of S by D of S. So overall transfer function is this: B of S, C of S, E of S, D of S, where so C of S by D of S. Okay, this is more. This is the flexibility we have. Okay, suppose so this is the system transfer function. Okay, so that means G of S is this one. So B of S by A of S. Okay, what are the poles now? If you make A of S equal to 0 and find the roots, they are the poles. Okay, so now as I said, stability means all poles should exist in the left of plane of the S plane. Okay, if any pole is existing on the right off plane of the S plane, we say that system is unstable. Now let us say, so if some poles are on the RHP side, RHP of S plane. Okay, so what from this what we can do generally, we could choose this roots of C of S because that is the controller we wanted to design. It means that we have the flexibility, let us say. So we could choose the roots of C of S, right? That thing we also call them as zeros. Okay. So in such a way that they would cancel with the roots of the or unstable poles of the A of S. Okay, that means we are cancelling by choosing C of S roots in such a way that they are going to cancel the C of S with A of S. Okay, similarly you choose D of S such that uh, all its roots will be on the LHP. So that means that overall what you are doing, so A of S, D of S, that is the denominator here. Okay, so that equal to 0. So you are choosing the C of S and D of S. All its roots would exist on the LHP, left of the S plane. That is the basic idea we can do. So poles cancellation as well as the choosing the poles properly. But here the issue is that even the unstable pole remains and the slightest noise and the disturbance will cancel out the output to grow until stopped by the saturation or system failure. Even if you go for the cancellation of the pole, the unstable pole still would remain, and if there is a slight change in the noise or disturbance, they will make the system response to grow without any bounds until it goes to the saturation or system fail. That's the disadvantage. Similarly, if the plant shows a poor response, okay, because of the 0 of B of S, if B of S roots, if any root is on the RHP, okay, so if you try to fix this B of S behavior by properly choosing the D of S, okay, just like the opposite case of A of S and C of S, now we are trying to see the B of S and D of S. This will also make the system unstable. Why? Because you're not changing the system behavior. You're just cancel outing the poles and zeros behavior. Okay, that makes the system still unstable. Okay, so that is about stability. Next, sensitivity. Suppose let us say your plant is having a we have seen the tracking error, we have seen the regulation, we have seen the stability, and this is sensitivity. Okay, let us say your plant we have a plant, okay, that has a gain of Z at a particular frequency. Okay, but when it is in actual operation, the gain may perturb, right? The gain may alter from G plus or minus to delta Z. Okay, so we can call this is as fractional change in delta, this term. That is nothing but delta Z by capital G. Okay, so we already know the open loop gain as this, because the plant G and controller GC, they are connected in this way. This is Y, this is R. Okay, so the overall transfer function L is nothing but G multiplied GC multiplied G. So that means this one. Okay, so now, so if you consider the perturbed system, it means that this loop gain, okay, so it changes. Okay, then you can add, you will be adding this change in the L of S. Okay, so you have L of S expression, sorry, you have L of S expression. So the and add delta L of S. Okay, you have this final expression. So from here you can find delta L of S as delta G of S GC of S. Okay, so now the sensitivity S term. So, okay, so this is defined as SLG. Okay, so of a transfer function L with respect to the plant Z. Okay, so that is defined as the fractional change in L defined as to the fractional change in G. Okay, so that is defined as SLG equal to dou L by L dou Z by Z. So which is written as Z by L dou L by dou Z. It means that simply, so the overall transfer function L, how sensitive that is with respect to the plant gain Z. If a plant gain G changes, okay, so what kind of change we could expect in the transfer function L? That is called as the sensitivity. Okay, SLG. So this is another important factor, okay, in the control systems. So total we have seen 4 things. So first one is tracking, next is regulation, next is stability, next is sensitivity. Okay, so we have seen these 4 cases with respect to these open loop systems. Okay, so open loop system is failed to do all these 4 cases. You can see it failed to perform all these 4 cases due to various reasons. Okay, so now let us consider this closed loop structure, where for the open loop structure, okay, so we are adding this feedback path. So we are adding this feedback path along with noise. So previously we have this structure. Okay, so now we are adding the noise as well as this feedback. Okay, to the open loop we are adding this feedback by using this sensor block as well as noise we are adding. Okay, so basically what this feedback control does is, so it uses a sensor here which measures the output. Okay, which measures the output, and that output will fed back to this summing point to compare with the reference signal. Okay, so now you could see we have 3 kinds of inputs. Okay, so let me remove this. Okay, we have 3 kinds of inputs. We have R of S, we have D of S, we have N of S. Okay, so using superposition theorem. So what is superposition theorem says? So superposition theorem says that when you have multiple input sources, okay, so the response in the response to a particular system, okay, is the summation of the responses when all those sources they are acting independently. It means that when R of s is acting, okay, so you could take d comma n 0. Okay, when d of s is acting, you could take r comma n 0. When n of s is only acting, you could take r comma d 0. Okay, so in all the three cases, so you will find y by r, y by d, y by n, and add all those three expressions. This is what you will get. The first expression, this one is y by r. This is y by d. This is y by n. Okay, so overall response is summation of so all these three responses. Okay, so now you have this control input. Control input is nothing but so the input which you apply here. Okay, the control input which you apply here. Okay, so that also in the same way. So the control input due to R of s, control input due to D of s, the control input due to N of s. So using the superposition theorem, so the total control input is the input due to individual inputs. Okay, now tracking error is nothing but so again in the same way. So E of s is nothing but your R of s minus YCL of s. Okay, closed loop system. So you will get that expression E of s as tracking error as so these expressions multiplied their inputs. I hope this is clear. So we got this E of s. Now getting into the same kind of analysis. So tracking error, stability, regulation, and sensitivity. So first start with the tracking error. So first to assume that these two are zeros, N of s and E of s 0. Then E of s expression becomes so the both these second and third term goes to 0. We have only the first term. Okay. Then so the tracking error if you so the tracking error if you consider so the tracking error if you consider now. Okay, so delta z of s for this tracking error for delta z of s, change in the open loop transfer function. Okay, so we can find E of s as delta E of s. Okay, so by including the delta term for this particular term. Okay, so now the change in the tracking error we can find as after substitution. So this term. So by adding into the E of s. Okay, so now so in this if you consider the this term and this term, okay, so when first term is greater than the second term, very greater than the second term, so we can approximate the function in this way. Okay, so then this g of s, okay, so let us call that is as L of s. Okay, finally you have this change in the tracking error. This suppose if you consider the large values for L of s, large values for L of s, okay, that will result in smaller changes in tracking error because L of s is in the denominator. Okay, for larger values of L of s, there will be a small change in the tracking. What is L of s? Basically, L of s is the multiplication of G and GC. What is G? G is the plant transfer function. GC is the controller transfer function. Plant transfer function and controller transfer function. Okay, so again consider the same example. So the example here is we have this reference input signal R of t. Okay, that is a ramp signal of slope 30 degree per second for a duration of 30 seconds, 0 to 30 seconds, and a steady state value of 300 degree Celsius. Correct? So now we are dealing with the closed loop system. What is our control strategy? So we have to design the controller which minimizes the error between the reference signal and the output, R of t and y of t, and that also minimizes the steady state error. Okay, so let us say in this example, okay, if we choose this one as the GC of S. Okay, so we'll see what exactly this expression is. If we choose something like this, something like k1 plus k2 by s, some expression for GC of S. If you apply and find y of t expression and find the steady state error. Okay, so this is the y of t temperature. Okay, so now you could see this. So the steady state error is almost 0. Okay, initially there is some error with small deviations, but when it reaches to this is almost 0. Okay, so this is due to the reason that due to the reason for the for the inclusion of the feedback. So whereas in open loop system, okay, this is not 0. Okay, this has got some value, it is not equal to 0, whereas in the closed loop system we got lesser tracking error. Okay, because the controller will have no control over the output here, so output in the open loop system, so that is tracking error. Next, sensitivity. Okay, so again recall the transfer function for the overall system by including all the 3 inputs. So the output of the system, again closed loop steady state gain. Okay, so closed loop steady state gain means, okay, you have this G, you have this GC controller, then you have this summing point, you have R here, you have Y here, so you're taking the feedback and giving it here. So let us consider this unity feedback system. So if you find Y by R, so you get GGC by 1 plus GGC. So that is this. So this we call it is as a closed loop feedback system. Okay. So now if you see the change, as I said, the sensitivity, how we define sensitivity is defined as SLZ. Okay, so that is dou that is delta L by L divided by delta Z by Z. Okay, so change in the L with when there is a change in G. Okay, so change in L due to delta Z. Okay, that is given by this expression. Okay, okay, so finally we can write delta closed loop steady state gain as this. Okay, so here we are trying to finding the sensitivity of the system. Okay, so sensitivity, how we are defining? So sensitivity of L with respect to Z. Okay, so that is nothing but, this expression is nothing but delta L by L divided by delta Z by Z. So same expression. Okay, so if you substitute all these terms here, so we are getting 1 by 1 plus GGC, where G is the plant and GC is the controller. G is the plant and GC is the controller. Okay, whereas in case of open loop system, so this is what we got. Okay, whereas in the closed loop system we have 1 by 1 plus GGC. Okay, so therefore in the feedback or closed loop control, okay, the error in the overall transfer function gain is less sensitive to the variations in the plant gain by a factor of this compared to the errors in the open loop gain. Okay, so here what it says, the error in the overall transfer function gain, that is less sensitive to the, the sensitivity is less compared to the open loop gain. Okay, so that is about the sensitivity of L with respect to the G, where L is nothing but the closed loop gain. Okay, next, stability. In the closed loop system, again I repeat, I think so we have this G, this is GC, okay, summing point, this is R, this is Y. Let's say here we have feedback as H. Okay, so if you properly write down the equations and find Y by R, okay, this is plus minus. Okay, so how can you write down the equations? Let me show you. So how can you write down the equations? So let's say this is error you get. This is the error you get. Okay, so what is Y? So here let us write one by one. Error E. E is nothing but R minus, okay, here H multiplied by Y. So this is the signal, it goes here and comes here. Okay, then what is Y? Y is nothing but error multiplied by GC multiplied G. Okay, so you could substitute E here. Once you substitute E, R minus HY, okay, multiplied GCG. Okay, so if you solve this and find Y by R, you'll get what? GCGH by, you'll get 1 plus GCGH. This is what you'll get. Okay, so this is this expression. Okay, so this expression in the denominator, okay, so this expression 1 plus GGC for H equal to 1. Okay, this is also called as the this equation is also called as the characteristic equation. Characteristic equation. Okay, now that characteristic equation, if you take the characteristic equation equal to 0, okay, you find the roots. Okay, so we call them as poles. These are nothing but the poles of the closed loop system. Okay, so now let us consider your G of S as B of S by A of S. Okay, the controller transfer function is C of S by D of S. So if you substitute into this 1 plus G of S, GC of S equal to 0, you get this expression 1 plus this expression. So finally simplification will leads to this. Okay, now you see this. So this feedback gives more freedom to the controller design than it does in the open loop system, where in the open loop system you have nothing, you have only this term. Okay, whereas here you have the full flexibility on this, full freedom for the controller design. Okay, so also so
Sir,
unlike the yeah
in that that Y by R in numerator H will not be there, no sir.
sorry, this one.
Yes, Y by R is equal to GCGH.
Just a minute. So you can check this. Yeah, it should not be there. Thanks. So it will be GC only 1 plus GCGH if you solve this equation. Yeah, thanks.
Okay.
Yeah, so compared to open loop case, so having pole A of S in the RHP, we said that if there is a pole in the RHP, what we are going to do, we tried for the pole cancellation for properly choosing this E of S there. Okay, here, so it's not needed. Instead, what you can do is having the pole A of S in RHP does not prevent the design of the controller that make the system stable. Okay, so you have the flexibility here choosing these expressions properly. So that is the advantage of defining the stability of the closed loop control system. Then, so let us see this example. Suppose if your g of s is this 1 by s square minus 1. So you're choosing b of s as 1, a of s as s plus 1 multiplied s minus 1. Okay, so now the let us choose the controller form as this. Let us say, okay. So the resulting characteristic equation. What is the characteristic equation? Again, 1 plus GCG equal to G. Okay. So you have this equation now. So let us say if you take gamma is equal to 1. Okay. So characteristic equation can be written like this. Okay, now if you are trying to finding the roots of this, okay, so they are nothing but the poles. Okay, you can change the poles location by properly choosing the or changing the value of k here. Okay, so by properly choosing the value of k, we can keep the poles or we can locate our poles wherever we are interested. Okay, so we can place the pole to our desired locations. So that is the advantage with the closed loop system. Okay, so next, these are the 4 cases we have for both the closed loop and open loop system: stability, tracking error, regulation, and sensitivity. So in all the cases, closed loop systems having many advantages. Okay, so then we will see a closed loop system having 2 more properties: the disturbance reduction and the noise reduction or noise attenuation. Okay, so first let us see here in first case. Okay, so as I said, take n of s, noise and the reference input are 0. Then we will have our tracking error consists only the disturbance. Okay, so in this, as you know already, L of s is nothing but GGC. Okay, so this expression is nothing but this is the sensitivity and G of s, and the input is D of s. Okay, if we fix this G of s, then by increasing the loop gain, okay, by increasing the loop gain means L of s, okay, you can reduce the effect of the disturbance. If you keep on increasing the L of s, you can reduce the L of s. Okay, so that is one advantage. Also, so as we know that the disturbance signal mostly they will be introduced at the lower frequencies. Okay, so for the purpose of the disturbance rejection, okay, so you could increase this L of s, okay, at lower frequencies only, so that the disturbance can be decreased. Okay, so this is equivalent like controller gain at the lower frequencies, that is decrease of sensitivity of the closed loop feedback system at lower frequencies only. Okay, next, noise attenuation. So similar way, you keep the D of s 0 and R of s 0. Okay, now the tracking error is given by this. So again, L of s is nothing but G and G of s. Okay, so now you see this term. Okay, so this term is called as the complementary sensitive function. Okay, so which is nothing but 1 minus the sensitivity. Okay, so if you have the very smaller value, so previously the disturbance, if you take more, the disturbance can be reduced. Now if you take the L of S is smaller value, so the noise can be attenuated smoothly. Okay, so just opposite to the disturbance signal, the noise may be introduced at the high frequencies. Okay, so for the purpose of the noise attenuation, what you can do is you could tune the loop gain, that is nothing but L of S, okay, to the lower values at a higher frequencies. Whereas for the disturbance rejection, we are doing everything at the lower frequencies, whereas for the noise attenuation, we do this at the higher frequencies. Okay, so the controller gain is reduced at higher frequencies for the noise attenuation. Okay, so now you can conclude the various differences between open loop and closed loop. So in the closed loop, we can improve the stability by properly choosing the poles to the desired locations. So you can decrease the sensitivity of the system to variations of the parameters. You can improve the rejection of the disturbances. So you can improve the reduction of steady state error. Okay, then improve the accuracy by measurement of the noise attenuation. Then you can also increase the bandwidth of the system, that is frequency range of the system. Okay, the basic disadvantages are you can reduce the gain of the overall system. Okay, so because we are including the feedback, so that may increase the cost and complexity also. So these are the basic comparisons between open loop and closed loop. With respect to these, stability, tracking, regulation, and sensitivity. Okay, because most of the control problems, okay, so they almost deal with these 4 topics, any control problem. Okay, so what we saw in this lecture is we saw the open loop controller design, closed loop controller and comparison, and we saw the 4 topics: tracking error, stability, sensitivity, disturbance rejection, and noise attenuation. So next what we do is now we saw that closed loop controller has many advantages. So we'll see the design of different closed loop controllers. So are there any queries here? Are there any quick queries?
Not right now, sir. It's actually there's a lot of information.
Yeah, it's a lot of information, but what you need to do is first see the overall picture and start asking the doubts. Okay, so first what you need to do is, let me show you once again. So these are the 4 major things: stability, tracking, regulation, sensitivity. Okay, so we are applying, assume these are the 4 tasks. Any control system problem will have these either 1 or 2 of these 4 tasks. Okay, so try to do the calculations with respect to the open loop, try to do the calculations with respect to the closed loop, and start comparing them, so that you'll have a clear idea why we have to go for the closed loop control system. Okay, so this is the practical aspect.
Okay.
Okay, so now the conclusion here is the closed loop systems will have many advantages over the open loop system. Okay, so we are getting into the controller design part of the closed loop system setting.
Sir,
Okay.
one doubt.
Yeah.
So in practice, we have some open loop systems also, no, sir, in washing machine kind of thing.
They are all open loop.
So
Because in open loop system, basically we give the signal, we will not have any control over the output.
yes, sir. So
If
in
disturbance
that,
is added, suppose we switch on the device.
okay.
Okay, if disturbance comes in the middle, So that will be reflected, its effect will be reflected in the output. We cannot reject it.
Oh, okay. So let's say in washing machine, when the machine is running, we open the door. That's counted as a disturbance, right?
Yes, yes, yes.
Okay. So how does the system deal with that? Mm. Oh, it will immediately stop.
Yeah, it will show its effect by going into the saturation of the system. Okay, it depends upon what you are doing. Okay,
Okay.
if you open the door, it may affect you maybe at a great negative way. Some disturbances are, I mean, very small, whereas some disturbances are very high.
Okay. No,
That depends.
let's say in top load washing machine, it's not it doesn't cause any damage, no.
Yeah,
So
that's what I am saying. That depends.
okay.
That depends what you are doing. Okay,
Oh,
so and based on the system also. Suppose if the fan is running,
okay.
so you put your regulator at 3, you're
Uh,
expected to get 1500 RPM.
okay.
Okay, so if you keep some stick in the fan,
Yeah, yeah.
okay, it will not run at 1500 RPM.
Yes, sir. Yes.
Okay, so if you keep some, I mean, some bending thing, it will not affect much. Where if you keep some iron rod, that will
Okay.
destroy the fan itself. Okay, it depends upon what you are doing, how the disturbance looks like.
Okay.
Looks okay in the practical systems. Suppose in communication and all, so the disturbances comes from the atmosphere. Maybe noise comes from the other systems. So the signal noise.
Okay.
These are, I mean, very high. Will have very high effect.
Okay.
Okay.
Yes.
So whereas once you getting into the closed loop system, they have the capability of rejecting these disturbances and attenuating these noise also.
Okay.
Okay, so that's why I said closed loop systems are more sensitive, but open loop systems are not very sensitive.
Okay.
Okay,
Thank you.
so yeah, so next we are looking into the controller design. Okay, so try to here the point is try to see how we are going for the controller design in what aspects. Okay, so in the previous lecture or previous session or previous module, okay, we have this table. Okay, so first what we did was uh, for a system, closed loop system, so there is something called as the error. Okay, then we have defined this steady state error. Okay, so after defining the steady state error, okay, for we also have defined the type of a system, which is called as the number of poles at the origin. Okay, then this is the tracking error. Okay, so for different inputs, for step, ramp, and parabolic. Okay, so we have defined the steady state error. Okay, we have defined the steady state error for when the type is 0, type is 1, type is 2. If you observe this, okay, for type 0 systems, only step input, okay, will produce some steady state error, that is 1 by 1 plus kp, where if you remember kp is nothing but what? Limit g of s, correct? S is tending to 0, correct? Then for
Yes, sir.
type 0, we cannot calculate this for ramp and parabolic, we cannot calculate the steady state error. Okay, next for type 1 system, so the steady state error is 1 by kV, where kV is nothing but what? kV is limit s is tending to 0, s g of s. Similarly, we have ka, limit s is tending to 0, s square g of s. These are the formulas we have. So for uh, type 1 system, only ramp input will produce some steady state error and step input will produce the 0 steady state error, and we cannot calculate this steady state error for the parabolic input. Similarly, for the type 2 system, we can only calculate the parabolic input, the steady state error, and for other two inputs, the steady state error is 0. This we have seen already in the previous module. Okay, so now, so see the controller part. What we are going to see here is the PID, proportional integral derivative controller. Okay, so in place of controller, we define this proportional integral derivative block, right? Which is a controller which continuously calculates the error between the R of t and y of t, R of t and this y of t. So it will try to adjust the control signal to minimize the error. Okay, so by adjusting properly these proportional integral derivative terms, we try to minimize the error. That's what we are going to see. First, what we do is we see individually how this proportional term, integral term, and derivative terms they will act on the system and changes their parameters in view of minimizing this error. Then finally, we will try to club all those three which has of this form. Okay, so where Kp, Ki, Kd are the proportional, integral, and derivative terms. Okay, let us start with the first one, proportional term. Okay, so basically what we are going to do here is, again I take the same block diagram. So this is G, this is Y. Okay, here in place of controller we have GC. Okay, the GC is nothing but these values. Okay, so this is R. So the question is, so we are going to take this GC as proportional controller, integral controller, and derivative controller, and see how it acts. Then we will try to club them and have PI controller, PD controller, then we will see the PID controller. So once we start checking these individually, what is P, what is I, what is T, you will get to know, or you will understand the you'll have the clarity, you'll get the clarity on the PI and PD. So if you understanding the basic controllers is must. Okay, so first, so what if you have a zero in the I mean, what if you will see the effect of zero and the pole. Okay, so first let us consider, okay, a transfer function g1 of s. Okay, transfer function g1 of s, so which has two complex poles and one zero. Okay, two complex poles are these and one zero. Okay, so we can write this one as by separating the terms. So first term and second term. Okay, you could see this. So here the 0 is located from here. You can see 0 is located at s is equal to minus alpha zeta omega n, and also it has this DC gain of 1. Okay, so now if you see the step response, that means this would be like y1 of s by r1 of s. Okay, step response means take r1 of s equal to 1 by s and find y1 of s. So g1 of s is 1 by s. So now you have g by s plus s by sigma zeta omega n g of s by s. Okay, you have this expression y1 of s equal to. So if you find take the inverse Laplace, you're getting what? Y1 of t equal to y of t plus 1 by alpha zeta omega n y dot of t. In this, Okay, if you take alpha is large, okay, which is far from the poles, and 0 will have little effect on the response. Okay, it means that if you take alpha, this is real part of S, this is imaginary part of S. Let's say, as I said, system has two complex poles and one 0. What is that 0 is this one. If you take alpha is very large value, that means very far from this here. Okay, so what this expression says is, okay, so it will have little effect on the system because of this term. Okay, if you take alpha is equal to 1, so the value of 0 will be very close to the real part of the poles. If you take alpha is here, that is very nearer to these poles. Okay, that will influence the response. Okay, so you could see here when alpha is equal to 100, this is not affecting much. Okay, so it is almost equal to the other output. This is not affecting much, so the deviation is very less. When alpha is very close to other poles and zeros. Okay, so this would be like, these are the poles you have. So this is with respect to alpha 0.5. Okay, and this is alpha is 100. Okay, so alpha very close to the 1 will have overshoot very high. So we know what is overshoot means. Overshoot is from the reference, so this magnitude. Okay, overshoot is very high. Clear? So that is for when zeta is equal to 0.5, when zeta is equal to 0.7, you'll have the similar effect. Okay, is this clear? So that is the effect of the 0 in the time domain specifications. What happened here? The overshoot is getting increased when alpha is equal to 0.5, that is very close to the poles. When alpha is equal to 100, so it has it is not showing much effect in both these cases. Clear? So that is the effect of the 0. Okay, so what is happening here? It is increasing the overshoot. There is not much change in the settling time. You can see all the curves are reaching almost at the settling time same time. Okay, then so response is faster. Okay, as alpha is tending to infinity. Okay, so the contribution of the 0 to the system response decreases and we recover the original signal behavior. Okay, so as alpha gets increases, we get the original system behavior. That is the effect of the 0. Similarly, we'll show the effect of adding extra pole, how it responds the system specifications. Okay, as the same g of s expression, we are adding this. This is added a pole. So added a pole at s equal to extra pole at s equal to minus alpha zeta omega n. So let's see when we add this. Okay, now you see this. So again, so when alpha is increasing, so what is happening here? So the response is the contribution of the pole to the system response reduces and we can recover the original behavior. Okay, so that means this behavior, okay, is nothing but this behavior. Okay, so the contribution of the pole is included more. Okay, for alpha is equal to 10. Okay, the response of the system with and without pole are similar. This part, sorry, this one. Okay, so yeah, so basically the original poles are at -1 plus or minus √2 by 2, so they are dominant, so they decide the system behavior. Okay, so basically what happened when you add a pole, okay, So when alpha is the pole value is very, very far or increasing, the contribution of the pole to the system response reduces and we recover the original behavior. Okay, so that is the characteristic when we add a additional pole. Okay, is this clear? So this is about adding a pole and adding a zero. Any doubt here?
No, sir.
Yeah, so now we are getting into the basic controller. So what, as I said, what we are doing is, this is your controller. So this is your controller. Inside this, we are keeping this KP, where KP is nothing but proportional gain. Proportional gain. Okay, so proportional controller gain. Okay, this is the structure. So in this structure, our main aim is to see what is y of t, and to check what happened to the steady state error. Okay, so that means to check E of t. What is E of t? R of t minus y of t. Okay, R of t minus y of t. Once we have y of t, we need to see steady state error. What is steady state error? Limit t is tending to infinity, E of t. Okay, that is the aim in every controller design, to check this one. Our ultimate aim is to match with the reference input, match our y of s to the r of s. Okay, so for that, what we do, first we'll find y of t and find the error and find the ESS. Okay, so we are starting with the proportional controller. Let's see what this proportional controller does. Okay, so the proportional controller input u of t is nothing but this one. So that is nothing but, here we get the error E of t. So E of t is nothing but what? R of t minus this signal. That we get E of t. Okay, so U of s is nothing but what? E of s multiplied by kp. So this is U of t, its time domain. So U of t is nothing but what? Kp multiplied E of t. So that is this one. Okay, so then controller transfer function. So what is the controller output? Output is U of s, input is what? E of s. Okay, what is the controller transfer function? That is kp. So that is kp. Controller transfer function is gc of s, here is kp. Okay, so let us start with the first order system now. Okay, with a unit step response, unit step reference. That means R of t would be 1, R of s would be 1 by s. So find E of s. So then our ESS is nothing but steady state error. Okay, so steady state error, how does it looks like? So we are supposed to, this is t, this is y of t. Okay, R of t is what? R of t is 1. This is what we wanted to meet. Okay, but what is the value here we got? Steady state error we have is k plus 1. It means the y of t expression would be like this. Okay, so if this is k, so this will be like k 1 by k plus 1. So always there will be a error, ESS. Okay, this error. Clear? So this is the steady state error we are getting. Okay, is this clear? Any doubt?
No, sir.
So what basically we are doing is, we are substituting kp here. Okay, So this is G. G is the first order system. So we find this E of S expression. Okay, we find this E of S expression. Once this E of S expression we have, we are finding ESS. That is nothing but what? Final value theorem of Laplace transforms. S is tending to 0, S E of S, correct? So that thing we are getting 1 by 1 k plus 1. Okay, basically we should get that as 0. But we are getting what? 1 by k plus 1. It means that non-zero steady state error we are getting. Non-zero steady state error we are getting. It means that y of t is not reaching 1. So there is a deviation. Okay. So now you could see. So it improved the time constant. Basically, the time constant here is t. So the time constant from t to t by 1 plus k because of this term. Okay. But it is giving a non-zero steady state error. This error. Okay. So how can we reduce that? The steady state error, how can you make that steady state error to 0? If you choose a large k value, okay, so you can make ESS to goes to 0, correct? So you can reduce that steady state error by choosing a larger k. But if you choose larger k, what would happen? If you choose very high value of k, okay, it can destabilize the system. It can destabilize the system. That is the problem. Okay, so we cannot choose larger k value of the system. So here we can also see the same analysis by adding the disturbance term also. Okay, what if your plant is like this instead of g of s here? Okay, so take your plant as 1 by j s square. If you take that, so your calculations will lead to the system is marginally stable. Okay, so that is for first order system. Let us see for the second order system. Okay, so this is the plant transfer function we have, a by s square plus a1s plus a2. Okay, similarly, once you find the closed loop transfer function, gcl of s equal to what is it, g by 1 plus gh. Okay, sorry. So GGC by GGCH. Okay. So what is the characteristic equation? Characteristic equation is 1 plus GGCH equal to 0. Okay. So this characteristic equation, if you do the calculations, you will get like this. Okay. After substituting G of S, this is the final equation. Okay. So here we have coefficient 1, coefficient a1, and this is the constant term. Okay, so by properly choosing the kp, okay, so we can control this constant term. Okay, by properly choosing kp, so which determines the natural frequency, but cannot control the damping term a1. Okay, as it is independent of the a2 and kp. Okay, it will not affect the much of the system behavior. So damping, it will not change. Only it can change is the constant term. Okay, so you can see here. So if you make that kp is very high, okay, so we could get this small steady state error. So the damping may be much too low for the satisfactory transient response without proportional control error. So you can see here. So if you choose your kp very high, you choose your kp very high. Okay, so you can make your system close to the value, close to the reference. Okay, so that is about proportional controller. Okay, so again consider the same example. What we wanted to do is to track a reference input R of t, okay, which has the slope of 30 degrees Celsius per second, okay, and having a steady state value of 300. So here our control strategy is to use this proportional controller. It means that controller box will have only this term, okay, that minimizes tracking error and steady state error. Okay, so we are starting with this G of S. Okay, control is GC of S is KP. Okay, closed loop transfer function T of S. Okay, so which is nothing but GGC by 1 plus GGC. Let us take unity feedback is equal to 1. If we substitute, so you will get this one because GC is KP G of S. Okay, now R of T is defined in this way. From 0 to 30, it is 30t. From 30 onwards, it is 300. Okay. Suppose if you see this system, T of S, it is a type 0 system. It means that you will have S power 0 here by S power 0. Okay. So, and the signal, this is a ramp signal. Okay. So we have seen the starting of these slides. So ramp signal, okay, type 0. Okay, what is that steady state error is infinity, correct? We cannot find or we cannot find the steady state error. That means it cannot track. Okay, so you can see starting we have so ramp signal, okay, type 0. So the steady state error is infinity. It cannot track that particular input. Okay, so you can see, so steady state error, so we are finding by after substitution. So for both the cases between 0 to 30 and 30 onwards, here steady state error is infinity, whereas here steady state error is this. Okay, for the ramp part, this is ramp part. Okay, this one is step. Okay, so suppose if you choose Kp is equal to 0.03. Okay, so we'll have steady state error of 10 degrees Celsius for T is greater than or equal to 30. And if you substitute here, and for between 0 to 30, the steady state error is infinity. Okay, so between 0 to 30, E of T will increases as T is increasing from 0 to 30 seconds. Okay, for the same system, the characteristic equation, if you consider, okay, so you will have after substituting Kp is equal to 0.03. Okay, you'll have this one. Okay, S square plus 1.1 S plus 3 equal to 0. So a proportional gain of Kp is equal to 0.03. Kp is a constant. Okay, so corresponding to the closed loop damping ratio of zeta 0.3. Okay, so here we'll get 0.3 zeta. Okay, which results in a constant DC offset of 10 degrees Celsius. Okay, so it means that we are getting a offset. Offset is nothing but your steady state error. Here you can see this. Okay, Kp is green one. Okay, so green one. So we are supposed to reach 300. Okay, this difference is 10. This difference is 10. Okay, suppose you can see here the steady state error is so almost reaching this 10. Okay, so we are getting that much offset. Okay, so that is the main part of the proportional controller. Okay, so summary with even if you include the step disturbance also, the error due to the disturbance will also decrease as the gain is increasing and damping will degrade. Okay, that is another advantage with the proportional control. Okay, so if you take the systems of larger order, increasing proportional gain will typically lead to instability for higher enough gain. Okay, so if you consider the type 0 system with the proportional control, will have a non-zero steady state offset in response to constant reference input, will not be capable of completely rejecting a constant disturbance input. So one way to improve the steady state accuracy of the control, okay, so without using extremely high controller gain, is to introduce this integral controller. Okay, because directly we are getting a offset, some offset from the proportional gain. Okay, so when you have systems of this nature, so adding a derivative controller will give an advantage. Okay, so here what we see is, so in these slides, so we have seen what happened if we add zeros, what happened if we add extra poles, and particularly the concept of the dominant poles. So adding a proportional gain term in place of the controller. Okay, any quick queries in this? What we will do is we'll stop here. Okay.
Okay, sir.
If you have any queries, please ask me, because you should get the controller, proportional controller basic concept.
No, sir.
Yeah. So
Actually,
yeah.
after yesterday's quiz, I haven't got time to.
Okay. You have not seen the videos. So only thing is that what you need to do is, so let me explain you once again. You know the closed loop control system, correct?
Yes.
So you have this plant transfer function. Okay. So I'm not considering disturbance here. So you have this controller transfer function. Okay. Then you have a summing point here, plus minus. Then you have a reference R of S here. Then you have Y of S here. Okay. So then you have the feedback here. Okay. So in this PID controller setting, what we do is, okay, we'll have the three things. Proportional controller, what we do is, this G of S we will replace with KP. Okay, in the integral controller, what we do is we will replace GC with KI by S. In the derivative controller, we replace the GC with KD multiplied S. Okay, so GC is given already for any problem, the plant transfer function. Sorry, G is given. GC is any of these. Okay, then what you need to do is, you already know Y of S by R of S expression, that is GGC by 1 plus GGCH, correct? So R of S is also known. It means that is the reference input which you wanted to reach. Okay, so then you find your Y of S expression. Okay, find your Y of S expression. So find this Y of S expression. Once you have this Y of S expression, apply the inverse Laplace and find Y of t expression. Okay, once you have Y of t expression, okay, t, Y of t, and this is the R of t you wanted to reach. Okay, R of t may be, it may not be straight line always, it could be some curve also. Let's say this is some kind of curve. This is R of t you wanted to reach. Okay, so then plot this Y of t. plot this y of t and see what is your steady state error. Okay, so check this steady state error. When you keep on changing the GC term with the KP, KI by S, KDS, and you will get to know all the differences. You will get to know understanding of the inclusion of the controller into the system. That is the major procedure for any controller. Is this clear?
Yes, sir.
Yeah, so that's what we did here also. So here also we did the same thing. So we started here. We have we took this KP, okay, and substituted here and found the error and found that the steady state error is 1 by k plus 1. Actually, it has to be 1, but we got we are supposed to reach 1, this 1 or k. We are getting 1 by k plus 1. It means both are not same. So that means that there is a non-zero steady state error. Okay, but it is taking our output very close to that. Okay, so it means that proportional controller will reduce the steady state error, but it will not make that steady state error to 0. Okay, that is the conclusion. Is this clear?
Yes, sir.
Yeah. Any other queries?
No, sir.
Okay, so we'll stop here and continue the next revisiting of next 2 lectures also on Wednesday along with the question paper discussion, and then Friday we'll solve some of the problems of the controller design, controller part. Okay.
Okay, sir. Yes, sir.
Yeah. Thank you.
Thank you, sir.